What's the parent function of the quadratics?
What's parent function?
Remember, parent function is the most basic one, the one that it kind of like starts from, and then once we
x squared.
transform it to f of x equals x squared. So this right here is what we call our parent function. I want you to write that in your notes. I want you to circle that and put that that is your parent function. So typically when we talk about transforming, we typically talk about what happened to the parent function. What's the change from the parent function? Sometimes, though, they do have you comparing two of them, and one of them is not the parent function, and you're just comparing what happened, what's the difference between the two. But typically, we are usually comparing to one quadratic function to the parent function, and saying, what would actually be the change here? So, compared to the function f of x equals x squared, our parent function, the quadratic function will become narrower or wider. So those are one of the transformations we're going to talk about. There are several transformations, by the way, that can happen. But at this level, we only have to talk about two of them. We're going to talk about, would the new parabola would it be skinnier, I like to say, because narrower is harder to say. So skinnier, would it be skinnier? Would it close in and get skinnier? Or would it widen out? Would it get wider? And then that depends on the value of a. So our a value tells us two things now. What's the one thing we already know that the a value tells us? The a value.
Oh.
So how many x squareds there are. So what if it's 2x squared? What does that tell us?
That there's
That it's going to open up. And what if it's negative x squared?
opens down.
That tells us it opens down because our a value is negative. So we already know that the a value plays the role of telling us if it's going to open up or if it's going to open down. Now we're going to add into that the a value also tells us, will it get skinnier or will it get wider? So it plays two roles. Okay? So we take the absolute value of a. In other words, we ignore the negative sign when we're talking about the width of it. So we say, depending on the absolute value of a, will it get wider or will it get skinnier? And then the other thing that we're going to talk about today is the other transformation is, it will translate up or down depending on the value of c. So what's the c value in the parent function? What's the c value in f of x equals x squared?
The point or the y-intercept.
Okay, and what is the y-intercept then of the parent function? What is the c value of the parent function?
Oh, 0.
0.
Yeah.
So if 0 is the y-intercept of the parent function, the c value, when it's not 0, tells us whether it's going to move up on that y-axis or down on the y-axis. So the c value has two roles now also. It's going to tell us where is it crossing the y-axis and how does that compare to what's happening in the other equation that you have that you're transforming it from? So let's take a look at this table that should be helpful to us. If the absolute value of a, I'm reading right here, if the absolute value of a is less than 1, the graph is actually going to get wider. It's going to spread out.
So if it's like negative 2, it'll be wider.
So if it's negative 2, the absolute value of negative 2 is 2, and 2 is greater than or less than 1?
Greater than, okay.
Oh, so is 2 less than 1?
No.
So would it get wider?
No, it would get narrower.
So give me an example of an a value that would make it get wider.
0.
Well, you can't have an a value of 0, we don't have a quadratic function, remember? So a, the absolute value of a has to be less than 1. So where do you suppose? What's the absolute value of negative 1? 1.
It's not
Is
equal
1
to-
less than 1?
No.
It has to be 0. Has to be, well, it can't be 0. Because if it's 0, then you'd have 0x squared, and then you wouldn't have an x squared.
It can't be negative because the absolute value of negative is positive.
So here's the deal, guys. I'm going to show you in a compound inequality. If the a value is between 0 and 1.
Oh, so like if it's like 0.5.
Yeah, it's 0.5 or 1/2.
Oh, no,
Then it's going to get wider. Okay, so if the a value is between 0 and 1, because what's the a value of the parent function, you guys? What is 1? The a value of the parent function is 1. So it can't be 1 or it would be the same. It wouldn't get wider, it wouldn't get skinnier. But if it isn't 1, then we say, oh, well, if it's between 0 and 1, if it's some fraction or some decimal number that's between 0 and 1, we know our parabola is going to get wider. And then it says, if the absolute value of a is greater than 1, so like Cassidy says, well, what about -2? Well, the absolute value of -2 is 2. So now, the absolute value of a is greater than 1.
So it could be.
So it's going to get skinnier then. So now, here's our parent function. And if a was a -2, now we know it's going to be opening down and it will get skinnier. Okay? So the bigger the absolute value of a gets, the skinnier the parabola gets, actually. The smaller the a value gets, if it's between 0 and 1, the smaller it gets, the wider it gets. It opens out more. So, and then the other thing, this is important for us to take note of also. For any change in a, the vertex and axis of symmetry don't move.
Okay.
The a value does not affect your vertex, and it does not affect your axis of symmetry. So, all it's going to do, remember, the a value's got 2 roles. It tells you whether it opens up or it opens down. It tells you if it's going to get skinnier or get fatter. Get skinnier or get fatter. So the a value has 2 roles. It doesn't move the vertex. It doesn't, and if it doesn't move the vertex, can it move the axis of symmetry? Tell me something about the relationship between the axis of symmetry and the vertex. What's always true? For $100, oh, I got Brian's attention now. And Darcy's. Their eyes at least looked up. For an imaginary $100, what relationship does the axis of symmetry and the vertex have to each other? Yeah, the vertex is always on the axis of symmetry, isn't it? So if the vertex doesn't move, will the axis of symmetry move?
No.
No. So those stay the same. Okay, so that's what we're going to be looking for with the a value. Okay, and then the c value. Now we're talking about the y-intercept, or the c value. If the c value is greater than 0, that means it's a positive number, right? If c is a positive number, it's where? Hey, by the way, where is the y-intercept for the parent function? Where'd you say it crosses? Where is it crossing the y-axis at? 0. In fact, where's the vertex for the parent function? At 0, 0.
Oh.
So it'll always be our vertex?
So, yeah, our vertex, whatever for the parent
So
function.
the parabola is always going to be in the middle of the graph.
Yeah. So when you have the parent function is always in the middle of the graph. It's sitting, its vertex is at the origin, and it's opening up. Always. Well, now if you change the y-intercept, or in other words, if it's not 0 anymore, now it's some positive number. Now it's got to cross the y-axis above the origin, so it's going to move that parabola up. So here it is at the origin, but c is no longer 0. So now it says it's a positive number, so that means it's got to cross the y-axis above the x-axis, so it's going to move your parabola up. Okay. So this time it does move the vertex, doesn't it? And it changes the y-intercept. And then if c is less than 0, what numbers are less than 0? What numbers are less than 0? Negative numbers. Well then, does that mean it's going to flip our graph over?
No.
No, only a does that, remember? So what's it going to do? What's it going to do? If c is less than 1, if c is a negative number.
Slim it down.
No, remember a is the fattening and slimming one.
It'll translate it up or down.
It's going to translate it up or down. Well, we said it goes up when c is positive, and it goes
Down when c is negative.
down when c is negative. Now it's going to move that vertex down on the y-axis, so it's below the x-axis. So now the vertex, so for any change in c, the vertex does change. It moves up or it moves down.
And my question is like, for a positive, if you have a positive and it moves up, does it mean you like leave the
our parent function below it. Yes. But notice if the vertex changes, remember, all we're doing is moving the vertex up or moving it down. So the axis of symmetry is still the y-axis. We didn't change the axis of symmetry. The only thing we're changing is the vertex by moving it up or down. The only way to change the axis of symmetry is if you move the vertex left or you move it right. And the good news is in Algebra 1 we don't have to worry about that, but in Algebra 2 we do. So we don't have to worry with, so the axis of symmetry is going to stay the same, but the vertex will move. Okay, so here's a couple of examples. Compare the graph of g of x. So notice it changed from being an f of x to a g of x. In other words, they're saying this is another quadratic function that we're going to compare to a function f of x. And so our new function is 1/3 x squared, and we're going to compare it to our parent function f of x equals x squared. So here's what they've done. They've graphed this one right here in the middle. That's our f of x, that's our parent function. And because a was 1/3, is that a positive or a negative, first of all? Positive, so it's going to open up just like the parent function does. And then because it's a 1/3, because it's between 0 and 1, should it get fatter or skinnier? Back up at your table.
Should get fatter. Or wait, what?
So
It's fatter,
Yeah.
because it's between.
yeah, because 1/3 is between 0 and 1, isn't it? So it should get fatter, and notice it did. It got wider. So here's our g of x equals 1/3 x squared, the one that I have in green. And did the c value change? No, only the a value changed. So the a value, because it went to 1/3, we can say that it's going to be wider than f of x. And we would say the vertex is the same. We could say one other thing here. What else is the same? What else could we say? What else stays the same when the vertex doesn't move? The axis of symmetry, yeah. The axis of symmetry is the same. So we're going to add that in there. Okay, and then we're going to add one more thing in there. We're going to say that both are going to open what? Up, yeah. So both open up. We're going to compare them that way too. So we're going to talk about everything that's going to happen by talking about the A and the C. So because the A was 1/3, that means it's positive. It's going to open up just like the parent function does. But now the A value is between 0 and 1, so that means it's going to get wider. The C value stayed the same, so that doesn't move the vertex. It stays right where it's at. If the vertex doesn't move, guess what? Neither does the axis of symmetry. In fact, we said the axis of symmetry is never going to move. The axis of symmetry should always stay the same in the transformations we're going to talk about. Okay, and then in this next one, we have h of x. Here's our transformed function. H of x equals x squared minus 4. It used a new initial now because we have a third equation. So we have x squared minus 4. And then we're going to compare it to the parent function. I'm going to change color on that. We're going to compare it to the parent function. So here's our parent function graphed again right here. And now we're going to say what happens because, did the a value change?
No.
No.
The B value.
So if the a value doesn't change, is that going to make it wider or skinnier?
No.
No. These are going to be deceiving though, because it looks like it got wider, doesn't it?
Only got wider because it drops down.
Yeah, the only reason it looks like it got wider is because it drops down. Because a is actually equal to 1 in this, so it doesn't get any wider or any skinnier. In fact, it still opens up and it's really got the same width. But the -4, our c equals -4, so that drops it down. What drops down?
The vertex.
The vertex, which in turn drops every point actually down also. So it goes down 4 units, and so h of x is translated down 4 units. The vertex is the vertex of f of x is 0, 0. The vertex of g of x is 0, negative 4. So we say where the vertex moved to. So it went from being at 0, 0 down to 0, negative 4. Did the axis of symmetry change? Okay, so the axis of symmetry stays the same. Does not change. And let's add in there something about the opening. What does it do?
So
Both open up. Okay, so both open up. Okay. Okay, so let's start doing some practicing of our own here. Compare the graphs of the functions below. And I have a graph there for us because I want us to see, you know, like, I want us to be able to visualize what it will look like also. Okay, so right now, let's talk about g of x. What does a equal? 2. What does c equal? Remember, we only have to worry about a and c right now.
I don't have a C.
We don't have a c, so what is it?
0.
0. Okay? And remember, in the parent function, a is 1, and c is 0 also. So just looking at the a's and the c's and just comparing them right now without even having a graph, tell me, what do you think will change? Are they both going to open the same way, or is one going to open up and the other one open down?
No, they're not the same way.
They're going to open the same way.
One's gonna be wider.
One's going to be wider or more narrow? Which one's going to be, we always want to compare to the parent function. So is our g of x equals 2x squared? Is it going to get skinnier or is it going to get wider?
Skinnier.
It's going to get skinnier because the absolute value of 2 is 2, and that makes, remember, whenever it's more than 1, it gets skinnier. Okay, so that's what our a value tells us, those two things. They're both going to open up. This is it. A stayed positive. And the other thing is g of x is going to be skinnier. It's not going to be as wide. Okay, now what does the c value tell us?
That it's not going to move up or down.
Okay, it's not going to move up or down. So it's not going to, the vertex is going to stay at the same location, isn't it? At 0, 0. The vertex is going to stay at 0, 0. Will the axis of symmetry change?
No.
No, that's not going to change either. Okay, so let's just, we should be able to graph these pretty easily without, and we're not going to, we'll use like the old, remember the old way you said you liked better the table? So let's do f of x equals, I'm going to have a pen in my hand. Let's do f of x equals x squared. Let's do that. Let's just make kind of a quick table over here for that one. So, when x, this isn't, we can do this math in our head. So we're going to go with, remember, if the vertex is at 0, 0, we already know that, right? We know the vertex is 0, 0, we know the y-intercept is 0, 0, so we know 0 is going to be in our table. So we're going to put that in the middle of our table. So we're going to do negative 1 and negative 2 above. We're going to do positive 1 and positive 2 below. So negative 2 times itself, what is that?
Negative 2.
No, negative 2 times itself, 4.
4.
Negative 1 times itself,
1.
1. 1 times itself, 1. 2 times itself, 4. There's our reflective, our symmetric behavior. Okay, let's go graph those 5 points. So 1, 1, and negative 1, 1, and 2, negative 2, 4, and positive 2, 4. Okay? So make your parabola for that one. And then I want you to put that this is f of x. You could just put f of x by it. You'll know that that's your parent function. Okay? Okay, now let's make our g of x, which is 2x squared. So Remember, whenever b is equal to 0, we know that the vertex is the y-intercept. And then when we have c equal to 0, we know that the y-intercept is 0. So guess what? Whenever there's not a b or a c value, in other words, there's 0, that is always going to have the origin as its vertex. So we can put that in the middle of our table again. So now let's do -1 again and -2, because these are points on either side of our vertex. I'm doing some math in our head here. It's 2x squared. We have to substitute in for x first, square it, and then take it times 2. So what's -2 squared?
Or positive 4.
Positive 4, and 4 times 2? 8. So when x is equal to -2, y is equal to 8. Okay, let's do -1. When x is equal to -1, -1 squared is 1, and 1 times 2 is 2. Okay, guys, when x is equal to 1, what's y gotta be? Not even doing any math.
2.
This is our vertex, reflective behavior. Remember our reflecting over?
Yeah, I said you're only after 0, they're only going to do anything.
Yeah, we can just repeat the behavior.
Can you write like one of them in markers so you can see the difference? Like,
Sure.
on
If
our
you want to
side.
do another one in another color, your pen or whatever, and then, because I can do it, of course, in a different color on here, but you are using a pencil. And I do have color pencils back in the drawer too, if you just want to grab those. Okay, and now we will, so we graph those 5 points, and we will connect, put a parabola going through them, and say this one is g of x. Okay, with our graph, I'm feeling pretty good right now about the things we said would happen. We said that the a value stayed positive, so we said both. So we're going to compare their graphs. Both open up. We're going to say that g of x, we're going to always talk about the new one. We're going to compare it to the parent function. So what happened? Did g of x get skinnier or wider? Okay, so g of x is, like I said, I like to use the word skinnier because it's easier to say. And there's how you spell skinnier. Or you can use the word narrower if you want.
Slimmer.
Slimmer, you could say it's slimmer, that works too. Okay, that takes care of our a value, right? Okay, now our c value. Did it move up or down? So the vertex stays the same. Vertex is same. And what is that vertex again?
0, 0.
0, 0. And then we also talk about the axis of symmetry. And the axis of symmetry is the same. In fact, we're going to say, what is that axis of symmetry? Remember, it's an equation. X equals,
Negative.
no, it goes through the vertex. What's the x value of the vertex?
0.
0. So it's x equals 0. Okay, so we compared our graphs. Okay. Holy cow, I didn't realize, I thought there was only a front on this.
No, there's a back.
There is a back.
We do the back tomorrow.
It might be, yeah. Okay, let's take a look at our next one. F of x equals x squared, what's that function again? What's it called?
Parent function.
Parent function, okay. What's the other one? It's the transformed function, okay? So, what's our a value for the parent function? 1. What's our c value?
C, 0.
0. Okay. What's our a value for the other function? 1. And what's our c value for the other function? 5. So, compare the functions of the graphs below. So what do you think should happen here? What do we predict? Is the direction of the opening going to change?
No.
No.
It's gonna move up.
Is the width going to change?
No.
No. Is the vertex going to change? Yes, it's going to do what? It's going to move up. Yeah, it's going to move up. Okay, so, did you leave yourself enough room? I didn't leave myself enough room over here, so I'm going to have to give myself, erase and give myself room again. So I need, oh, I didn't really need, what I could do is just look at the other side over here. Our parent function is always going to have this table, isn't it? We already have that table. We already got that one, so we can just graph that. In fact, it should get to the point that we should be able to graph these almost without looking at what after you do enough of them. There's our parent function, f of x equals x squared. We already have a table for that one. We don't need to create it again. But we do need one for our h of x. So we have h of x equals x squared plus 5. Okay, so we need x, y. Is our vertex going to be 0, 0 this time? What do we say is going to happen?
It's gonna move up.
It's going to move up 5. If it moves up 5, what would our vertex have to be at? 0, 5. So we're going to put 0, 5 in the middle of our table, because the vertex is in the middle of the parabola. And we're going to say, okay, I got to do -1 and -2. And then I got to do +1 and +2. And remember, if the vertex moves at 5, every other point moves at 5 also. So anybody think they can predict what the y value is going to be when x is equal to -1? 6. Because all we have to do is add 5 to our 1 over here, don't we? Okay, let's see if that works. -1 squared is 1. 1 plus 5 is 6. Okay, so let's look at our y value in the parent function. When x is equal to -2, y is equal to 4. So what's it going to be equal to for this one? 9. Okay, and now we can repeat the behavior down here, can't we? We have to work very hard. So in other words, we're putting our critical thinking skills to work here. If it's only moving up, then every point has to move up that much. The x's aren't changing, only the y's are, and they're changing by 5. So now we put our new vertex, oops, that's a 6 and a 5. And graph our other points also. And make your new parabola. And again, is it going to look like, remember we said the width won't change, right? But is it going to look like a change? It is going to because we moved it up. So we're it does appear that it did, but because the a values didn't change, they both still open up. Same width, right? They don't change, they both really are the same width.
Axis of symmetry is still the same.
Okay, well, let's do the vertex next. The vertex is moved up how many units?
5.
Moved up 5 units. And so now it's at, we already did it in our table, 0, 5. And then we say the axis of symmetry is the same. And what is that axis of symmetry again?
Sure.
X equals 0. So, the A values, opening, width. We talk about those two things. C value, moving the vertex, and and the axis of symmetry. Okay? Okay, so any questions on these? Okay, let's go see what's on the back. Okay, it says compare by graphing. Okay, well I think we can, and then, so here what they're doing is they're combining something happened to A and something happened to C. They've already done the graph for us. We should be able to keep going on here. Because, so basically what we're still doing is we're still identifying, okay, A is equal to 1 here, and C is equal to 0. So we just compare. A is equal to 1/2, C is equal to -3. So we should be able to do this without having to graph. We should be able to look at that and say, okay, since A is 1/2, now instead of 1, the graph got wider. Because remember, if it's between 0 and 1, it gets wider. They both open upwards, because the A values are both positive. I'd like the order of these turned around. I would write these differently, but the axis of symmetry stays the same. The vertex changes though. It goes down 3, so it is now at the location 0, -3. Okay, so now what they're going to have us practice here is, can we just do this without graphing? Okay, so I'm going to leave that example for you to study on your own. And let's look at number 3. They've already got a graph for us. But we should be able to, even without the graph, we should be able to tell what happens. So, what's our A value in g of x? -2. And what's our C value? -1. In our parent function, A is 1, C is 0. So remember, we're going to have 4 things we're going to talk about. So what do we say? G of x does what? Opens
Up.
down.
Down.
G of x opens down. And f of x opens up. The A value also tells us something else. A went from being, so the absolute value of 1 is 1, and the absolute value of -2 is 2. So now it's bigger than 1, so does it get skinnier or fatter?
Here's
Skinnier. So g of x is skinnier, slimmer, more narrow. Okay, those are the A value. That's what the A value does for us. What does the C value do? Okay, remember the vertex. Is the vertex the same? No, it moved it down. So the g of x, the vertex is at what?
-1.
Is at 0, -1. So it moved it down. Moved down 1 unit. Moved from being at 0, 0 to 0, -1. It moved down 1. And then how about the axis of symmetry?
Stays the same.
Axis of symmetry stays the same. Axis of symmetry is x equals 0 for both, we can say. Okay, so the real goal is to be able to just tell what's going to happen to the graphs without ever having to graph. So that's what we're going to practice here next. Number 4. So, what's the first thing you guys want to do always? What did I say? Identify the A and the C. A equals 1/4. C equals 4. A equals 1. C equals 0. Okay, no graphing. Remember, we start with the A. They both open up. Both open up. Because they're both a positive A. And he also tells us something about the width. Because g of x have the same width, get skinnier, get wider. It's wider. G of x is wider because its a value is between 0 and 1. So that's our a value. Now our c value. How about the vertex? Does the vertex of each of them the same? Nope.
No.
The vertex moves
Up 4.
up 4. So it becomes 0, 4. And our C value also tells us
Axis stays the same.
axis stays the same. Axis is, you know what, I'll let you just say axis instead of symmetry. That's a lot of writing, isn't it? Axis is x equals 0 for both. Axis of symmetry. We're going to understand that we mean axis of symmetry there, okay? Okay, any questions about that one? So we have 4 bullet points every time. After we identify the A and the C. So let's do h of x. What's our A value? -5. And our C value is? -1. And our parent function, A equals 1, C equals 0. Okay. Do they both open up?
No.
No. So h of x does what?
Opens down.
Opens down. And f of x opens up. So one's going to be an upside down U, the other one's going to be a right side up U.
H of x is slimmer.
H of x gets slimmer because
It's negative. Or the greater value.
the absolute value of -5 is 5, which is greater than 1, so it's going to get skinnier. Okay, C value. Vertex stay the same?
No.
Are both vertices at 0, 0? No, the vertex of g of x moves down or up.
So the H of x.
Oh yeah, h of x vertex moves, sorry, h of x vertex moves
Down.
down. How many units?
1.
1 unit, because it's a negative, that makes it move down, and -1, so we say it moves down 1 unit. So where's it at?
0, -1.
At 0, -1. And how about our axis of symmetry? And so it's what? Axis is
X equals 0.
x equals 0 for both. Okay. That one's going to get a little redundant. We want to get that so planted in our brains that when we do transform it left or right, we remember when we have to do that. Okay.